Welcome to solverfy.
Once again, welcome to a new problem. We have two identical masses. So this is the information that's given. It's such that we have two identical masses. One is sliding down a circular path. It's almost like a roller coaster. So we have one sitting here. We're gonna call this A, and then there's another one sitting here. We're going to call this B. So at the beginning, and oh yeah, something else is that we're also given that the radius of this circular path happens to be R. And so that's the information we're given, that the masses are identical. So MA is exactly the same as MB, which is exactly the same as M. And then also, we have the initial velocity of A right there. And then they're going to collide, eventually these two masses. This is kind of like before. And then this is what happens after. So they slide and collide with each other down here. And then they pick up, and end up having, as they're moving upwards, um, the they have a final velocity, a final combined velocity of A and B. That's the final combined velocity. A B also has its own initial velocity. So let's just make sure we have the numbers right. So the initial velocity of B, as you can see, is 0 meters per second because it's not moving right now. But when they collide with each other, we're going to have a final velocity, a combined final velocity. So they move upwards all the way, and then they're going to stop. So they stop at some point right here. Okay, and when they stop, their final velocity happens to be 0. So VA plus B, VA plus B equals to 0 meters per second. When they stop. We don't have to call this final. Let's just call it the velocity of A, combined velocity of A and B. So this is the information that we're given, and we want to find this height, h. Okay, that's the height we want to find. And so, how high they both go when they collide with each other. So we're going to start the problem in the next page, and we'll use the law of conservation of energy, which says this is for mass A. So this one is mass A, as you can recall, this one right here. So we're coming back and saying the initial kinetic energy of A plus the final, the initial kinetic energy of A plus the initial potential energy of A equals to the final kinetic energy of A plus the final kinetic energy, or rather the final potential energy of A. So that's what we're given, and you can see that this radius will give us the initial height from the base of the circular path. So this is going to be r. So coming back, we see that the initial kinetic energy is 0. Okay, so 0 joules. Since we're starting right here, it's stationary. So that means the initial kinetic energy will be 0. And then times the mass of A times the acceleration due to gravity and the radius. This radius is the same as the initial height of A, and that's the replacement we have there. And then the final kinetic energy of A is 1/2 mass of A times the velocity of A, the final velocity of A. Okay, so we want to get the velocity of A squared. That's going to be squared at the bottom. So final velocity of A at the bottom. This is right here. So when it collides, just before it collides, A has a final velocity. And then A and B will have an initial velocity. And then A and B will also have a final velocity. So that's kind of what's happening in this problem. And then plus the height, when they collide, this height right here is at 0 meters. So it means that even though we have we're thinking about a potential energy, but at the base, the potential energy is 0 joules. So then we end up having a mass of A, gr, equals to 1/2 mass of A, final velocity of A. These two cancel out. And then we divide, this is squared, we divide both sides by 1/2. And so we end up having the final velocity of A squared equals to, this 2 comes up, so it's going to be 2 gr. So the final velocity of A here is just the square root of 2 gr, like that. So we can leave it that way or that way. And then the next thing we want to do is going to happen on the next page. So on the next page, we think about the law of conservation of momentum of the system, which says that the initial momentum of the system equals to the final momentum of the system. And here the initial momentum is the mass of A times the initial velocity of A plus the mass of B times the initial velocity of B equals to, when they combine with each other, we have the mass of A plus the mass of B times the, so this is before they collide, and then this is after they collide and stick with each other. So it's just going to be a final. They're eventually going to stop anyway. So we have the initial momentum of the system has to be the final momentum. So just before after they collide, they stick together, and this will give us the final velocity of B, of A and B, when they combine together. And so remember, the initial velocity of B is 0. So this part is going to be 0. And then we have, we want to compute the combined velocity. That's our target. We want to compute the combined velocity. So V of A plus B final equals to mass of A, velocity of A, all over mass of A plus mass of B. And so this one becomes, remember when we were on the other page, we were able to solve the velocity, the final velocity of A final. We were able to solve A final. Remember, A is is coming down. So this actually is A final. If you can recall, this is the final velocity of A right here. This one right here. We're calling it the final as it just before it collides. And so the initial, actually, instead of calling it final or initial, we're gonna have the so the the velocity. Yeah, this is final velocity. This is before collision. This is before the collision. We have the final velocity of A and the initial velocity of B. And then this is after collision when they stick together. The initial, so this should be initial like this. The initial of A and B, yes. So this is the initial of A and B plus the final of A and B. Yes. So this is how we have it. This is how we have it. And our goal is to compute the initial before it stops, before the system stops. So this is going to be initial right here. So coming back, just making sure that our conventions are right. This is the final when they stop. This is the final right here when they stop. This is the initial. This is the initial for B by itself, and this is the initial for A by itself. And then this is the final for A just before they stop right here. So just before they collide. So this is what we have in the problem. So we're going to plug in MA, VA, VA final just before they collide. This is VA final before they collide because we changed this to VA final equals to radical 2 GR like that. And then we're dividing that by MA plus MB. But if you can recall, MA and MB is equal to M. So this is just 2M. This is just 2M. And also, since MA equals to M, we can replace that with M, and these two are going to cancel out. And so we have, we're left with, in the next page, we have VA plus B initial equals to, going back, radical 2 GR all of 2, which is the same as 4 radical GR all over 2, which becomes 2 which becomes so they're going to cancel out because this 2 comes out. When it comes out as 4. So this is, the m's cancel, so this is 2 radical GR like that. Okay, 2 radical GR. So once again, we just want to make sure that our steps are right. We have this block mass up here, and then it slides all the way up until down, collides. Before it slides, the initial velocity is 0. And then the final velocity, we have to compute that just before it strikes. And then they stick together and collide. They collide and stick together. And the final velocity up until the maximum height is 0. We don't know what the initial velocity is. We have to figure that out. And so we're using the law of conservation of energy. The initial energy of the system is equal to the final energy of the system. Initially, we have the kinetic energy of A is 0 because the initial velocity of A is 0. And then we have the also this is for mass A, if you can recall. We have the initial potential energy, which is MAGR, and then the final, when it's sliding downwards, is that at the base level. Remember, there's no height, so it's going to be zero potential energy. We solve, we get the final velocity of A. And then we move on and use the law of conservation of momentum. Initial momentum of the system equals to the final momentum. Initially, the total momentum of the system for A, it's ma va final just before collision. But then the initial velocity of B is zero because it's sitting still. And then when they collide, they're going to have an initial momentum and a final momentum. The final momentum will be zero because the final velocity is zero. So we compare that. We want to get the initial combined velocity when they stick together, and that happens to be, that's what we're looking for. We have the mass of A and the velocity of A, and then the mass of B and the velocity of B. So we compare this side to that side and solve for that initial combined velocity of A and B. So mass of A over velocity of A final, which is radical 2gr, over mass of A plus mass of B. These m's are going to cancel out, and so we're left with a square root of 2gr all over 2, square root of 2gr all over 2. Alternatively, we can do it a little bit differently. We could say this is the square root of 2gr all of 4. You could do it that way, which becomes the square root of gr all over 2. That's how we could do it. We can move this 2 inside and it becomes 4, and then we simplify. This is 1, this is 2. So the initial velocity of A and B combined is a radical gr all over 2. And then in the next page, we're going to use still the law of conservation of energy to get the final height, law of conservation of energy. And this is when the two blocks are sticking together. So we have an initial position where h is 0, and then we have a final position where we don't know what h is. So then the initial kinetic energy of A and B, initial, plus the initial potential energy of A and B equals to the final kinetic energy of A and B plus the final potential energy of A and B. At the initial level, the height of A and B, the initial height of A and B is 0. This is the final height of A and B. So if the initial height is 0, this is going to be 0. When they stick together, the initial velocity, when they stick together, we're going to compute the initial kinetic energy. So going back, we have, just before they stick together, the initial, we do have the initial the initial velocity, so we can get the initial kinetic energy. The final kinetic energy will be 0 because the final velocity of the two items or the two masses, when they stick together, the final velocity is 0. If you go back right here, you see that this final velocity when they stick together is 0. So we have to account for that. And so we have the initial kinetic energy of the system being equal to the final potential energy of the system. The initial kinetic energy is 1/2 ma plus mb va plus b. That's the combined velocity, initial velocity squared, equals to mass of A plus mass of B, and then G, and also the final height of A and B final, like that. Okay, so we're getting close to solving the problems. These two are going to cancel out because they're the same, and then we have to move G to this side. So on the next page, we're going to have the height of A plus B, the final height of A plus B becomes equal to, if I go back to this page, 1/2 times the initial velocity of A and B. And so the final height of A and B together is 1/2. Remember, the initial velocity, or the initial velocity of A and B, was square root of gr/2. So that's what we have to plug in right here, square root of gr/2. This one happens to be squared, so you have to remember that. This one is squared, don't forget that. And then this 2 is going to be squared. So that final height of A and B final, when it stops, is simply 1/2 times radical gr/2, which is the same as 1/2, times, this is squared, so it's going to get rid of the radical, and so our final height is gr/4. So a lot of variables involved in this problem. You could see that we have the initially this mass has a velocity of 0, and so its initial kinetic energy is 0, and then it slides downwards. It's going to have a final velocity just before it collides. The initial velocity of B is 0. Once they collide, they stick together, so they have a common initial velocity. Their common final velocity will be 0. That's the information we have, and so we have to compute the final velocity of A before collision. And so here we focus on mass A. The initial kinetic energy is 0 because it's not moving, since its initial velocity is 0. And then also, but the initial potential energy, because it's elevated a distance of r, is going to be magr. The final potential energy is 0. It does have a final kinetic energy just before collision, and so we get the final velocity, which is radical 2gr. Then we use the law of conservation of momentum of the system before and after. Before collision, A has a momentum, okay, and that momentum is due to its final velocity. But B doesn't have a momentum because its initial velocity is 0. When they collide, we have an initial momentum for A and B combined, but we don't have a final momentum. It's 0 because the final velocity is 0. So we use that to get the initial velocity of A and B when they stick together and collide. And that's going to be in the next page. You see we get radical gr/2. And so moving forward, we can use the law of conservation of energy. This is for the system A plus B when they stick together. So initially, the height is 0 when they stick together, and we want to find the final height. The kinetic energy, the initial kinetic energy of the system, is premised on the initial velocity of the system. But then the initial momentum of the system A and B is 0 because this height is 0. So that cancels out. The final kinetic energy is 0 because when they stick together, it stops right there. So that's going to be 0. We use that and solve for the initial combined velocity of A and B. We're going to use that initial combined velocity and compare that to the final potential energy of A and B. And in the last step, we end up solving for the final height. Hope you enjoy the problem. Feel free to send any questions and have a wonderful day. Okay, thanks. Bye.